Welcome. I'm going to show you how to solve a friction problem using free body diagrams. And you'll see I've got a bunch of steps written out here because these are kind of complicated. And if you get stuck, it kind of falls back on these steps. And notice that in each step, I've kind of highlighted a couple of things so that you know like what you can kind of like think of them like free body diagram, data, mass is not weight as steps that kind of remind yourself. And I'm going to do these in rainbow colors, and who knows how well this is going to show up. I tried to pick colors that will be distinctive, but we'll see. All right, so I'm going to do the first one in green. Okay. I'm going to draw a free body diagram. So what we have here is a box that's being pulled horizontally across a desk. And we need to know what forces are on it, right? So we'll start with this one. Is there a gravity force? Yep, because there always is, and it's straight down. Okay. Is there a surface supporting it? Yes, it's a flat surface. So the normal force will be perpendicular to that flat surface or straight up. Remember, normal means perpendicular. And then Miss Noma's pulling it across a desk. So that is an applied force. So she's pulling it. I'm going to make it pull to the right. Here comes the cat. Dude, you can't be here right now. I love you, but you can't. Hang out on the bed here. Okay. And then finally, there's no strings involved, so there's no tension, but there is a friction force, which is parallel to the surfaces in contact and opposite motion. So since I'm pulling to the right, the friction is going to be the left. And that's it. Okay, the reason free body diagrams is its own step is because it's critical to name the forces. And the reason for that is that you need to have formulas. And if you have no names for your forces, because you just wrote like a number next to them, you won't be able to draw the formulas and you're missing a key step. So that's why so for that reason, I've made making data a completely separate step. Okay, I'm going to do it in maybe turquoise. I don't know. Here we go. Okay, so what are the data? Well, we know the spring scale is 25 newtons. Okay, we know the mass of the object is 5 kilograms. All right, we're looking for the coefficient of friction. Okay, now there are coefficient of frictions on your reference tables, and a hint that you might need those in a problem is if they very specifically talk about what the things are. So if they're like wood on wood or rubber on dry concrete, this is a hint that you need to use this table, but that is not what's going on here. We've got a lab table that we don't know what it's made of, and a box of books that's made out of cardboard. That's not here. So we're going to have to calculate it a different way. Okay. That's it. Done with the data step. And again, I make this a separate step because if you don't label your forces with names, it's going to set you up for problems later. All right. Now, the third one is key. Mass is not weight. We've talked about all the ways that mass and weight are different. And in order to, so the way these problems go, they might give you the force of gravity in newtons, or they might give you the mass. If they give you the mass, you're going to need to calculate the weight because you're going to need that. And if they give you the force, you're going to need to calculate the mass if it's accelerating. It turns out if it's in equilibrium, you end up not needing the mass. So this is its own step. Okay. You will, if they give you the mass, you're definitely going to need the weight for a friction problem. And if they give you the weight, you might need to find the mass to later put into F net equals MA. All right. This time they gave us the mass, so let's go ahead and calculate that. So F sub G is 5 kilograms. It's about 10 pounds times 9.81. And since down is negative, I'm going to put a negative in here. And when I do the math on that, I get that this is about negative 49 newtons. I'm going to circle that because it's a intermediate calculation. Okay, that's done. Now, many years I'll do a diagonal force, and there are going to be a couple simple angled things that you'll see, but we're not going to have a complicated problem from start to finish that involves the diagonal force, not this year. Okay, so this I'm going to say is NA for right now. And so we're not going to do this because there's no diagonals. Okay, so we don't need to do this. I've wasted my favorite purple color on something we're not even going to do. Lame. Okay, now we're going to do specific forms of F net equals MA. Now, this is both the step that everyone gets stuck on and forgets. So if you are stuck on a problem, you're like, I don't know what to do next. It's writing specific forms of F net equals MA. This is the whole point to our diagram. Okay, the reason we draw the diagram, which is always a little different, is so that then we can use these formulas, which are always the same, and like write a specific thing that's tailored to each problem. So we need to do it twice. Once for the perpendicular direction, actually, once for the x direction, once for the y. I'm glad I said that. Parallel and perpendicular are only helpful on inclined planes. Don't use parallel and perpendicular on the flats. Okay, we do need to do this twice, once for the x direction and once for the y direction. And again, the reason friction problems have this is because the frictional force depends on the normal force, so automatically you have two directions that you have to deal with. Now, looking at my picture, I look at this and I say, all right, how many forces are acting up and making up that net force? Remember, net just means sum of all the forces. So I've got a frictional force, which I'll expect to be negative, and a force applied. I'm not putting the numbers in yet because you need formulas, equals MAX. Now, since this is going at constant velocity, this is not accelerating. Okay. And this is similar to what you did in that lab where you were pulling things with a little recording device. All right. In my y direction, I have two formulas as well, or two forces as well. Force normal and force gravity equals MA in the y direction. And this is not even moving in the y direction, so that's also going to go to 0. Okay. And now we're going to go to our final step, which I guess I'll do in, does pink show up well? I'll do it in pink. Got a lot of warm colors here. Okay, so now we're looking for this coefficient of friction. And the way these friction problems go is there's three formulas you end up using. This one here, the one you did for the x direction, the one you did for the y direction, and the third formula is FF equals mu Fn, which is the frictional formula off your reference tables. Okay, about a third of the way down on the mechanics page. So if you can't kind of figure out how to identify the unknown and work backwards, then just start plugging into these three formulas you made. But ideally, we'd start here and go backwards. So in order to get mu, I need the force of friction over the force normal. Okay. And what we're finding here, by the way, is we're finding kinetic friction because this is moving. So before I can do that, though, I need both the frictional force and the normal force, which is what this is all about. Okay. So looking here, I'm going to just start plugging numbers into here. So I've got frictional force. Just kind of divide this up. Plus force applied equals 0. These are balanced, okay? But they're not always going to be balanced for every problem, which is why you need to go through this step, okay? And so since the frictional force plus 25 newtons is 0, so the frictional force ends up being a negative 25 newtons. Surprise, surprise. They're balanced, all right? And then here I have, and I realize these wouldn't be balanced if this was accelerating, but in this case, it's not accelerating. All right, and then in the y direction, I have the normal force, and the weight force is negative 49 newtons equals 0 as well. And so the normal force is a positive 49 newtons. Okay, once I have those two, I can then go and put them into here. So I did this first. Then I did this, and then lastly, I'm plugging into here. All right, so moving this down a little bit. Okay, I've got that mu equals the force of friction, which is negative 25 newtons, all over the force normal, which is 49 newtons. Now, mu has no sign. I'm making mu, not a u. No sign and no unit because the newtons cancel out. Okay, so and then yeah, it has no sign. There's no such thing as a negative mu. So technically, you're taking the free body. You're taking not the free body. The absolute value of this that is not on your reference tables. This is something you just need to know. 25 over 49. I'm going to do that in my head. Mu is about 0.5. This is a reasonable number for mu. I like you also to do a reality check. Notice that mu's are almost always between 0 and 1. It is conceivable to have a mu that's greater than 1. That would be akin to like really sticky rubber that can sit on an incline greater than 45 without slipping down. All right, but most typical things have a mu between 0 and 1. Really slippery things, like a wax ski on snow, have a really low mu. And things that are more sticky, like rubber on dry concrete, has a higher mu. Remember, I said that mu is, think of it as like a measure of stickiness. Okay, this is our final answer. Let's just kind of remind what we did because we went through a lot of steps. Okay, we did a free body diagram labeling all the forces. We filled in all the given data. Okay, we did mass is not weight and we used the mass to find the weight, and we might have instead needed the weight to find the mass. Then we used the free body diagram to write our two equations, okay? And those are always going to be a little different, just like the free body diagrams are always a little bit different. And then by solving these two equations that we wrote and the friction formula, we were able to then plug and chug and find our unknown. All right. We got 3 problems like this for homework. Good luck.